We talked about the moment of inertia for point particles, but we haven't said anything yet about what happens if we have a continuous object, like a ball or a cylinder or a disk or, or something more abstract. So the way we can find that is this. So let's look at if we just have a single mass that's traveling at some, distance. So this will be mass 1, some distance r1 from the center. Okay? So the moment of inertia is just equal to m r1 squared. Now let's say we add a second mass. Same distance. So the moment of inertia now, we just add the moments of inertia together. So we have 2 times m r1 squared. Okay? And let's say we just have a whole bunch of these, right? Well, we know the moment of inertia is just the sum of each mass times the distance to the point of rotation squared. Well, in every case, since they're all on the circle, they all have the same distance, r1 squared, times the sum of all the masses. So in other words, the sum of the masses, big M, times r1 squared, is a moment of inertia of all of the masses. Okay, so that means if we have a whole bunch of masses that are all the same distance away, that this is the new moment of inertia. Now what happens if we have a continuous object? So instead of a bunch of points, we have something that's like a hoop, right? So it's so we have kind of this hoop that goes around. Well, it's basically the same thing. We'll divide this up into a small segment, and that small segment has a mass dm. Okay, but we remember that density is mass divided by volume. So if we have some mass dm, the density is going to be that divided by the volume of this little tiny block, dv. So in other words, dm is equal to the density of the hoop times the velocity. I'm sorry, not velocity, the volume. So the moment of inertia, we go from this sum over I of m sub I, distance squared, now becomes an integral of dm r squared, which is an integral of the density r squared times the differential volume dv. Okay, so this actually working this out isn't going to be on your exam, but for example, just to show quickly like how this would work for a hoop, if we say that it has just a constant density rho, then we see that the moment of inertia becomes rho, the integral of r squared, dv is just basically d theta, and so you'll get, if you actually work this out, you'll see that this is just mass times r1 squared, which is exactly what exactly what you would expect it to be. So it's the mass of the hoop times r1 squared. Okay, but using this formula as an integral and working this out, you can get more complicated results. So for example, like here are, most books, and you can find these all over the internet, are these tables that have just the moments of inertia for different objects. So here's an example. And so on the exam, you'll actually just be given this. So if you're given a sphere, you'll be given that this is the formula for the moment of inertia of a sphere. If you're given a hoop, here's the formula for the moment of inertia of a hoop. If it's a shell, if it's a rod, all those will be given to you. So you don't actually need to memorize those. You just need to understand how to use them. And so, yeah, so I guess that's all we have to talk about for a moment for continuous objects.